Imagine standing on a riverbank roughly 13,000 years ago, watching the ice retreat for the first time in your entire life. The world had been locked in an ice age for tens of thousands of years, but finally, after millennia of brutal cold, the planet was warming. Glaciers were shrinking. Forests were creeping northward. Rivers that had been frozen solid for generations were beginning to run free again. And then, without warning, in a shift so abrupt that scientists still argue over exactly how fast it happened, the warming reversed completely. Temperatures crashed back down to ice age levels within what may have been a matter of decades, and in some regions, the drop may have happened even faster than that. This wasn't a gentle slide back into winter. This was the climate equivalent of slamming on the brakes at full speed. Scientists call this event the Younger Dryas, and for 1,200 years, Earth stayed locked in this sudden deep freeze, refusing to finish the thaw it had already started. And to this day, the exact cause remains one of the most genuinely disputed mysteries in all of climate science. To understand how strange this event really is, you first need to understand how climate is supposed to change. Normally, the transition out of an ice age is slow, gradual, and gentle, unfolding across thousands of years as Earth's orbit and axial tilt shift the planet's exposure to sunlight. This is climate change measured in millennia, not lifetimes. But the Younger Dryas broke that rule entirely. Ice cores drilled deep into the Greenland ice sheet preserve an extraordinary, frozen record of ancient atmospheric conditions, layer by layer, almost like the rings of a tree. And when scientists examined the layers marking the start of the Younger Dryas, what they found was staggering. In some interpretations of the data, temperatures in the North Atlantic region may have dropped by as much as 10 degrees Celsius within a single human generation. Some researchers have argued certain shifts may have occurred in a span as short as a single decade. To put that in perspective, that's a climate shift roughly equivalent to Britain's current average temperature abruptly dropping to match modern-day Siberia and staying there for well over 1,000 years straight. Picture what that would have actually felt like on the ground. A hunter-gatherer band living along a river valley in what is now northern Europe would have spent their entire childhood watching the world slowly warm and soften around them. Forests were expanding. Game was becoming more abundant. Life, by the standards of the retreating ice age, was genuinely improving year after year. Then, within the span of that same person's adult lifetime, everything reversed. Rivers they had fished for years began freezing solid again in seasons that had once run warm and open. Forests that had only just begun creeping into their territory started dying back, retreating south as fast as they had once advanced. Herds of animals that depended on that vanishing vegetation would have been forced to migrate, taking with them the very food sources entire human communities had come to depend upon. This wasn't a myth passed down through vague oral memory. This was lived, physical, generational experience, etched permanently into the ice itself. So what actually caused Earth's climate to slam into reverse this dramatically? For decades, the leading, most widely supported explanation has centered on a single massive lake, one so enormous it doesn't even exist anymore. As the great ice sheets covering North America began melting at the end of the Ice Age, meltwater collected into a colossal body of water known to geologists as Glacial Lake Agassiz. At its largest, this ancient lake may have held more fresh water than all of today's Great Lakes combined. For a long time, an ice dam held this staggering volume of water in place, but ice dams don't last forever. Many researchers believe that dam catastrophically failed, releasing an almost unimaginable pulse of cold, fresh water directly into the North Atlantic Ocean in a geological instant. Here's where the real science gets genuinely fascinating, because the ocean doesn't just passively absorb a shock like that. The North Atlantic is home to a critical circulation system, sometimes called the Great Ocean Conveyor Belt, which carries warm water north from the tropics and helps regulate the climate of the entire surrounding region, including much of Europe. This system depends heavily on saltwater density, since denser, salter water sinks and helps drive the entire circulating current forward. A massive sudden influx of cold, fresh meltwater could have diluted that saltwater balance dramatically, and in doing so, potentially stalled the entire circulation system almost in its tracks. If that current genuinely slowed or briefly collapsed, The warm water that normally keeps the North Atlantic region mild would have simply stopped arriving. The result would be exactly what the ice cores actually show: a sudden, severe, and remarkably long-lasting regional deep freeze. This meltwater theory remains the most widely accepted explanation among climate scientists today, and it fits a genuinely impressive amount of the available physical evidence rather well. But it isn't without serious problems, and this is exactly where the story takes its first controversial turn. Critics of the meltwater theory point out a frustrating, persistent issue. Geologists still haven't definitively located the precise outflow channel that Lake Agassiz floodwaters would have needed to travel through to reach the North Atlantic Ocean in the first place. Multiple possible routes have been proposed over the decades, through the St. Lawrence River Valley, through the Mackenzie River system further north, and researchers continue actively debating which pathway, if any single one, actually carried the flood. Some scientists have even suggested the flood may have traveled through several different routes at different points in time, rather than through one single catastrophic channel. This uncertainty matters enormously, because if we can't reliably pin down exactly how and when the water actually reached the ocean, we can't fully confirm the timing lines up precisely with the abrupt cooling event itself. And that persistent uncertainty is exactly what opened the door to a second, far more controversial theory, one that has generated genuine, sometimes fierce scientific argument for well over a decade now. In 2007, a team of researchers proposed something genuinely startling: that the Younger Dryas wasn't triggered by meltwater at all, but by a cosmic impact. According to what's now called the Younger Dryas Impact Hypothesis, one or more comet fragments may have exploded above or struck the North American ice sheet almost exactly at the start of the cooling event, roughly 12,900 years ago. The proposed evidence includes a distinct layer of unusual material found at Younger Dryas boundary sites across multiple continents, including elevated concentrations of platinum, tiny nanodiamonds, and microscopic spherules of melted rock, materials researchers argue are more commonly associated with impact events than with any typical natural earthly process. If true, the implications here are genuinely dramatic. A massive cosmic impact striking the ice sheet could have thrown enormous quantities of pulverized ice, dust, and debris high into the atmosphere, blocking significant sunlight and triggering rapid, severe global cooling almost immediately. Proponents of the hypothesis have also argued that such an impact could independently help explain two other major, long unresolved mysteries from roughly the same time period: the sudden, mysterious extinction of North American megafauna, including mammoths, mastodons, and giant ground sloths, and the equally abrupt, poorly understood disappearance of the Clovis culture, one of the earliest well-documented human populations in the Americas. Under this theory, one single, catastrophic cosmic event could potentially explain three separate ancient mysteries all at once, tied together by a single moment in deep time. It's a genuinely compelling, dramatic story, the kind that understandably captures public imagination and headlines fast. But here's where we need to be scrupulously honest about where the actual scientific consensus currently stands, because this specific hypothesis remains deeply, genuinely contested within the broader research community. Multiple independent research teams have attempted to replicate the original impact evidence at various boundary layer sites around the world, and a significant number of those replication attempts have failed to reliably reproduce the original findings. Critics have argued that some of the claimed nanodiamonds may actually be a different, far more common carbon structure that simply resembles nanodiamonds under standard laboratory analysis. Other researchers have pointed out that no confirmed impact crater dating precisely to this exact time period has ever been definitively located anywhere on Earth, despite roughly 2 decades of dedicated searching by multiple international teams. For an impact large enough to meaningfully disrupt global climate, many scientists argue we should reasonably expect to find much clearer, more unambiguous physical evidence somewhere by now. So where does this genuinely leave us today? After more than 15 years of continued, often heated scientific back and forth on the subject? The honest, unglamorous answer is this: the meltwater hypothesis remains the leading, best-supported explanation among the majority of working climate scientists, but it has never been fully, conclusively proven beyond all reasonable doubt either. The impact hypothesis, meanwhile, continues to attract a smaller but genuinely persistent group of dedicated researchers who argue the specific chemical and mineral signatures found at Younger Dryas boundary sites still demand a fuller, more complete explanation than conventional meltwater alone can currently provide. Some scientists have even proposed hybrid explanations, suggesting a smaller, more modest impact event might have helped destabilize the ice sheet in ways that then triggered, or at least significantly accelerated, the meltwater flooding process described in the primary theory. This remains genuinely unresolved, contested scientific territory, and any documentary claiming total, absolute certainty on this specific question, in either direction, isn't being fully honest with its audience about where the real science currently stands. What we do know with genuine, high confidence is what this abrupt climate shift actually did to human life on the ground at the time. Across Europe, populations that had begun expanding northward as the ice retreated were forced into rapid, difficult retreat right back toward the south, abandoning territory they had only just begun to settle and rely upon. In the Near East, some researchers argue the sudden onset of colder, drier conditions may have played a significant role in pushing certain hunter-gatherer populations toward deliberately cultivating wild cereal grains for the very first time, as reliable wild food sources became increasingly scarce and unpredictable. If that connection holds up under continued scrutiny, the Younger Dryas may have inadvertently helped push humanity toward the earliest beginnings of agriculture itself. One of the single most consequential turning points in our entire species' history, potentially forced into being by a period of genuine, sustained climatic crisis. And then, just as abruptly as it began, the deep freeze ended. The Greenland ice core record shows the Younger Dryas terminating with a warming event potentially even faster and more dramatic than its initial onset. Some interpretations of the ice core data suggest temperatures in the North Atlantic region may have rebounded by several degrees Celsius within a span of less than a decade, an almost unbelievably rapid climatic swing by any normal geological standard. Whatever process had stalled the ocean's critical circulation system apparently switched back on again, almost as suddenly as it had first shut down. Within a few generations, forests began reclaiming the territory ice had only recently retaken. Rivers thawed permanently, and the long, slow, final transition out of the Ice Age, the one interrupted so dramatically 12 centuries earlier, finally resumed and continued through to full completion. This is precisely what makes the Younger Dryas such a genuinely important, cautionary case study for scientists studying our climate today. It stands as concrete, undeniable, physical proof that Earth's climate system is fully capable of shifting dramatically within a single human lifetime, not merely across the safely distant span of many thousands of years. Whatever the ultimate root cause turns out to have actually been, meltwater, cosmic impact, or some genuinely complex combination of contributing factors, the underlying physical mechanism remains deeply relevant to modern climate science. Our own oceanic circulation system today depends on remarkably similar physical principles, the same fundamental balance of temperature and salinity that may have been catastrophically disrupted roughly 13,000 years ago. Some climate researchers have expressed genuine concern that modern glacial meltwater, pouring steadily into the North Atlantic from a warming Greenland ice sheet today, could theoretically risk destabilizing that same critical circulation system once again, though the specific scale, timing, and likelihood of any modern parallel remains a genuinely active and ongoing area of serious scientific research and debate. So here's the question worth sitting with as we close out this story. If Earth's climate could reverse itself this violently, this quickly, and for reasons scientists still can't fully agree on after decades of dedicated research, what does that genuinely tell us about how stable, or how fragile, our current climate system might actually be beneath its calm surface? Do you think the answer ultimately lies in a vanished glacial lake, a fragment of comet from deep space, or perhaps in some combination of causes we simply haven't fully pieced together yet? And if a freeze this sudden and severe happened once already in relatively recent Earth history, what quietly tells us it couldn't, in some form, happen again?